Hello students, so today we are going to study about one of the application of Gauss law, and using the Gauss law we will find the electric field due to spheres. Now to find the electric field due to spheres, first we will study about spheres. Now this sphere, it can be divided into two parts, hollow and solid, and these hollow and solid spheres can further be categorized into two parts, that is conducting, non-conducting. And this solid sphere can again be categorized into two parts. First one is conducting and the second one is non-conducting. Now, what is the difference between hollow and solid sphere? If you take a real life example, so for hollow sphere, we will take a plastic ball. And you know that if you cut the plastic ball from the middle, you will see that it is completely empty from inside. So that means hollow sphere is completely empty from inside. And if you take the example of solid sphere, so suppose if you take a sponge ball, or most of you call it as a stress ball, that sponge ball, if you cut it from the middle, you will see that it is not completely empty from the inside. It has some mass inside, some volume inside. It is not empty from the inside. So this is the difference between solid and hollow sphere. Now, hollow sphere can be divided into two parts, conducting and non-conducting. Same solid sphere can also be divided as conducting and non-conducting. And in case of conductors, we know that whatever charge we give to a conductor, that charge always reside on the surface of the conductor. So if we take a hollow conducting sphere and if we give any charge to this sphere, then these charges will reside only on the surface of the conductor. And what about hollow non-conducting sphere? Since this hollow non-conducting sphere, this is a hollow sphere and it is also non-conducting. That means since it is completely empty from inside, so in case of hollow non-conducting sphere, in this case also whatever charge we give to the sphere, hollow non-conducting sphere, that charge will also reside on the surface of the conductor. Same case will happen with the solid conducting sphere, because in case of conductors, charges always reside on the surface of the conductor. So if you take an example of solid conducting sphere, in that case also, the charges will reside only on the surface. Now, if you take a solid non-conducting sphere, then in this case, since it is a non-conducting sphere and solid sphere is not empty from inside, that means whatever charge we give to this sphere, they will be distributed throughout the volume of the conductor, throughout the volume of the conductor. So we can say that the electric field due to a hollow conducting, hollow non-conducting, and solid conducting sphere will show the same pattern, and we will use the same derivation for all these three spheres. But the electric field due to solid non-conducting sphere will have some different pattern, will have some different variation. So we will have to use some other derivation method for the solid non-conducting sphere. So first we will find the electric field due to hollow, conducting, non-conducting and solid conducting sphere using Gauss law. Now there is a question, what is Gauss law? All of you have studied that Gauss law states that the total electric flux through a closed surface, total electric flux through a closed surface is equal to total charge enclosed by the closed surface divided by epsilon naught. And this total electric flux can also be written as closed integral of E dot dA. That is the total electric field. This is the electric field due to all the charges dot dA equal to total charge enclosed inside the Gaussian surface divided by epsilon naught. This electric field is due to all the charges present inside and outside the Gaussian surface, but this is the total charge enclosed inside the Gaussian surface only. So now we will find the electric field due to hollow conducting, non-conducting and solid conducting sphere. Now We will find the electric field at a point A, which is inside the sphere, at point B, which is on the surface of the sphere, and at point C, which is outside the sphere. So here, suppose we give some charge Q to this sphere, and we know since it is a hollow conducting or solid conducting sphere, so the charges will reside on the surface of the sphere. And since it is also a hollow non-conducting sphere, that means in this case also the charges will reside on the surface of the sphere. Now we have to find electric field at point A, which is inside the sphere. Suppose it is at a distance r from the center. Now, for inside point, we can say this small r is less than capital R, which is the radius of the sphere. Now, here to find the electric field at point A, we will use the Gauss law. So, what we do in Gauss law, we will choose a Gaussian surface passing through that point A, which is at a distance r from the center. We will choose a Gaussian surface, a spherical Gaussian surface, which will pass through point A and at a distance r from the center. Now, what is Gauss law? Gauss law is closed integral of E dot dA, that will be equal to Q enclosed divided by epsilon naught. Now, here, as we know, electric field will be radially outward due to all these charges. It will be radially outward. Electric field due to a sphere is radially outward due to a positive charge. So we can say at point A, or we can say at every point on the Gaussian surface, will be equal because the electric field line or the point is at a equal distance from the center on the Gaussian surface. Each and every point on the Gaussian surface is at equal distance from the center. So we can say the electric field will be constant, and we will choose an elemental area here. We'll choose a elemental area dA, and the area dA vector will be in this direction. That means the electric field and the dA are in the same direction. Electric field vector and the dA vector are in the same direction. So we can say, we can write it as E dA cos of 0, that will be equal to Q enclosed divided by epsilon naught. Now here, as we know, electric field is constant, so we can take it out of the integration sign. This will be Q enclosed divided by epsilon naught. Now, what will be the value of closed integral of dA? Now, suppose if we take dA and add all these dAs, we will get the total surface area of the sphere. That means it will be equal to 4 pi small r square, because the radius of the Gaussian surface is r. Now, what is the total charge enclosed in the Gaussian surface? Now, as I have already told you, in case of hollow conducting, non-conducting, or solid conducting sphere, charges always reside on the surface of the sphere. That means here the total charge enclosed inside this Gaussian surface is 0. So this will be equal to 0. That means the electric field at point A or inside the sphere is 0. Now we will find the electric field outside the sphere at point C. Outside r greater than capital R radius of sphere. So what will we do? We have to find the electric field at point C, which is outside the sphere, which is at the distance r from the center. So we'll choose a Gaussian surface. We'll pass to the point C, which is at a distance of r from the center. We'll choose a spherical Gaussian surface passing through point C, and each and every point on this Gaussian surface is at a distance r from the center. Now again, we will use the Gauss law to find the electric field. We know that closed integral of E dot dA, that will be equal to Q enclosed divided by epsilon naught. Now here, as we know, if we choose a Gaussian surface like this, dA, it will be pointing outward. So we can say the electric field and the dA vector are along the same line. That means the angle between them will be 0 degree. And each and every point on this Gaussian surface is at a distance r from the center. That means we can say electric field is constant. So we can take electric field out of the integral sign. So this will be integral of dA. Q enclosed. And what is the Q enclosed? The total charge enclosed within this Gaussian surface is capital Q divided by epsilon naught. So this will be equal to E. dA will be, integral of dA will be 4 pi small r square. That will be equal to Q by epsilon naught. From here we can say electric field that will be Q divided by 4 pi epsilon naught r square, or we can write it as K Q divided by r square. And we know that this is the electric field due to a point charge. That means we can say if we have to find the electric field at any point outside the sphere, that means we can assume that the total charge is concentrated at the center, and then from there we'll find the electric field using this formula kq by small r square. Or we can say if we have to find the electric field at any point outside the sphere, which means that this sphere behaves as a point charge such that total charge is concentrated at the center. Now, what will be the electric field at the surface? This is the electric field at point C. Now at surface, which means R will be equal to capital R. Now for this, what will we do? We'll put R is equal to capital R in this formula, and we will get the electric field at point P, which is at the surface. That will be equal to KQ by capital R squared, or Q upon 4 pi epsilon naught capital R squared. Now if we draw the graph for the electric field versus distance for this sphere, that will be, this is 0. This will be somewhere R equal to capital R. Now the electric field between this, when R is less than capital R, the electric field is 0. That means the graph will be like this. At the surface, the electric field has some value, that is K into Q by capital R square. And after this, R greater than R, this is small r greater than capital R, the electric field varies as 1 by R square. So the graph will be like this. Electric field is inversely proportional to small r square. Now we have to find the electric field due to solid non-conducting sphere. As I have already told you that it is a solid non-conducting sphere. It is a solid sphere, that means it is not empty from inside. So whatever charge we give to the solid non-conducting sphere, the charge will be distributed throughout the volume of the sphere. So here we have given the charge Q to this sphere, and this charge Q will be distributed throughout the volume of the sphere. Now we have to find the electric field at point A, which is inside the sphere, at point B, which is on the surface of the sphere, and at point C, which is outside the sphere. So the first point is we will find the electric field inside the sphere, that is R less than capital R, that is at point A. Now, again, to find the electric field at point A, which is at the distance of R from the center, we will use Gauss law. We will consider a Gaussian surface, a spherical Gaussian surface, which will pass through point R, and each and every point on this Gaussian surface is at a distance R from the center. That means the electric field here will be radially outward. We know that electric field, it will be radially outward at each and every point. Now, this is the electric field. Now, to find the electric field, we will use Gauss law, that is closed integral of E dot dA That will be equal to Q enclosed divided by epsilon naught. Now here we know that here we will choose a Gaussian elementary area, that is dA, and this area vector will also be in the outward direction. That means we can say the angle between the electric field and the dA vector will be 0 degree. So we can write it as integral of E dA cos 0, and cos 0 will be 1. That will be equal to Q enclosed divided by epsilon naught. Now each and every point on this Gaussian surface is at a distance r from the center. That means electric field is constant. So we can take it out of the integration sign. That will be closed integral of dA Q enclosed by epsilon naught. Now, what is the value of closed integral of dA? If we choose dA and add all these dA, we will get the total surface area of this sphere. That will be 4 pi small r square. Now, since here the charge is not only distributed on the surface, it is distributed throughout the volume of the sphere. That means here we have to consider a term called as volume charge density. Volume charge density, which is denoted by rho. Volume charge density means volume charge per unit volume. Charge per unit volume. Now, for this sphere, for this solid sphere of radius capital R, the value of rho will be the total charge is Q, volume is 4 by 3 pi R cube. Now this is the value of rho for the whole sphere. Now, what is the value of rho for this small sphere, this Gaussian surface? Now, the Q enclosed. Q is enclosed within this Gaussian surface. We are talking about this Gaussian surface. So the total charge enclosed within this Gaussian surface is not capital Q. Capital Q is the total charge enclosed within this sphere of radius capital R. But we are talking about the total charge enclosed within this Gaussian surface of radius small r. So that will be rho into volume of the Gaussian surface, or volume enclosed volume of the sphere, Gaussian surface, divided by epsilon naught. That will be rho into, or we can write it here, it will be E into 4 pi small r square into rho into volume of this Gaussian surface. That will be 4 by 3 pi r cube divided by epsilon naught. From here, 4 pi will get cancelled out, r square will get cancelled out, and we will get E will be equal to rho into r by 3 epsilon naught. And we know the value of rho is Q upon 4 by 3 pi r cube. That will be Q upon 4 by 3 pi r cube into 3 into epsilon naught into r. Now this 3 and 3 will get cancelled out, and we get the value as Q into r divided by 4 pi epsilon naught into r cube. So these are the two important formulas for the electric field inside the sphere, that is at point A. This one and this one. Now we have to find the electric field outside the sphere, that is at point C. Outside means r greater than capital R, radius of sphere. Now again, to find the electric field at point C outside the sphere, we will choose a Gaussian surface which will pass through point C and which will be at a distance r from the center. In this case, this will be capital R, small r. Now, again, the electric field, the formula we will use is closed integral of E dot dA Q enclosed divided by epsilon naught. Now, again, the electric field will be radially outward, and if we choose a elemental area like this, the dA vector will be outward. That means the angle between the electric field and the dA vector will again be 0. So we can write it as E dA cos of 0, and cos of 0 we know that it is equal to 1. That will be Q enclosed by epsilon naught. Now, since electric field is constant because each and every point on this Gaussian surface is at a distance of small r from the center, that means the value of electric field will be constant. So we can take it out of the integration sign. That will be closed integral dA is equal to q enclosed by epsilon naught. Now, what is the value of closed integral of dA? That means if we add in each and every dA, we will get the surface area of this sphere. That will be 4 pi small r square. Now this time, what will be the value of Q enclosed? Now we know that Q enclosed is the total charge enclosed within the Gaussian surface. This one is the Gaussian surface, this outer one is the Gaussian surface, and the total charge enclosed within this Gaussian surface is over this volume only. This volume of sphere having radius capital R. So we will write it as rho into volume of this sphere of radius capital R. That will be 4 by 3 pi R cube. Why we have chosen this volume? Because the total charge is enclosed over this volume only. There is no charge here. There is no charge here. The charge is enclosed within this sphere only. That's why we have taken this volume. 4 by 3 pi r cube divided by epsilon naught. So here 4 and 4 pi will be cancelled out and we will get E is equal to rho into r cube divided by 3 epsilon naught r square. And we know that rho we can write it as q divided by 4 by 3 pi capital R cube into 3 into epsilon naught into r square into r cube. Now this r cube will get cancelled out. This 3 and 3 will get cancelled out and we will get the electric field as q divided by 4 pi epsilon naught r square or k q by r square. This is the electric field at point C. Electric field at point C. Now we have to find the electric field at the surface, that is point B. At surface, that is R equal to capital R. Now what will we do? In either of these formulas, we will put small r equal to capital R and we will get the formula EB is equal to K Q by capital R square or 4 Q upon 4 pi epsilon naught R square. Now you can check one thing here, that whether it is a solid non-conducting sphere or a solid conducting hollow conducting non-conducting sphere, whenever we have to find electric field at a point outside the sphere, then we will assume that the total charge is concentrated at the center and the point is at a distance of a small r from the center, and we will use the same formula kq by r square, whether it is a solid conducting, solid non-conducting, hollow conducting or non-conducting sphere, only for the outer point. Now if we draw E versus R curve, then we can say that this point, let it be 0, this will be R equal to capital R, this distance is R less than R, and this one is R greater than R. Now, as we know, for the inside point, R less than capital R, the electric field is directly proportional to small r. We can say electric field is directly proportional to small r because Q, 4 pi, epsilon naught, capital R are constant. So we can say it will be a straight line. Now at the surface, the value of electric field is kq by capital R square. Now outside the surface, again the electric field is varying at 1 by R square. So the graph will be like this. Here E is directly proportional to R. Here R is inversely proportional to R square. Now we have already seen the electric field due to a solid and the hollow sphere. Now let's do a question based on the solid non-conducting sphere. So in the question it is given that we have a solid non-conducting sphere of radius capital R, which is having a. Now we have discussed about the electric field at various points due to hollow and solid spheres. Now let's do a question based on the concept of non-conducting solid sphere. So a solid non-conducting sphere of radius r has a volume charge density that varies as rho is equal to rho naught into r. Till now we have seen that the volume charge density was rho and that was constant. But here the charge distribution, the volume charge density is not constant. It is varying as rho is equal to rho naught into r. That means whatever charge that we give to the sphere, it is not uniformly distributed throughout the volume. Somewhere the charge will be more, at some points the charge will be less. Like it is not uniformly distributed throughout the volume of the sphere. And we have to find the electric field inside, outside, and at the surface of the sphere. Again, we will first find the electric field inside the sphere, that is R less than capital R. That means we have to suppose this is the center O. We have to find the electric field at point A, at point B, and at point C. Now, this is the distance R. We have to find the electric field inside the sphere at point A, which is at a distance of R from the center. That means we will again choose a Gaussian surface which will pass through the point A and which will be at a distance R from the center. Now, what does Gauss law say? E dot dA, that will be equal to Q enclosed divided by epsilon naught. Now, here, as we know, the electric field will be radially outward. The electric field, it will be radially outward like this. That means if we choose a dA vector, again the dA vector will be radially outward. That means the electric field and the dA vector will have an angle of 0 degree in between them. So we can say E dA cos 0, that will be Q enclosed divided by epsilon naught. Now, since each and every point on this Gaussian surface is at a distance r from the center, that means electric field is constant, so we can take it out of the integration sign. So that will be closed integral of dA equal to Q enclosed divided by epsilon naught. Now from here, the closed integral dA, that will be 4 pi small r squared. Now, here is the main question. What will be the value of Q enclosed? Since here, we cannot use Q enclosed is equal to rho into V. Simply like this, we cannot use because the rho is not constant. Rho is varying as rho naught into R. That means as the value of R from the center increases, the value of Q will change at each and every point. That means if we take this R, this much distance, the value of Q will be different. If we take this distance from the center, value of Q will be different because the value of rho is changing as rho naught into R. That means we cannot directly use Q enclosed is equal to rho into V in this formula. So what will we do? In this case, as the volume charge density is varying, we will use integration and we will use a cell, an elemental cell to find the electric field. How will we do that? This is our sphere. Now, here from the center at a distance x, we will assume an elemental cell of thickness dx, of thickness dx. Now, here the value of Q enclosed, it will be rho into dV, close integral of rho into dV, where dV is the volume of this elemental cell. Now, how to understand this? We will take an example of an onion. Suppose if we take onion as a sphere, then we know that onion is made up of a number of layers. If we take out each and every layer of the onion, then that each and every layer will behave as an elemental cell. Now here, the rho will be rho naught into x as the value. Here we have taken till distance x from the center. What will be the volume of this sphere, this elemental cell? That will be, if we take out this cell like this, its radius is x and thickness is dx. Now, if we take an example of onion, this, suppose this is a spherical cell. Now, if we open it like this will become the area of the surface area of the elemental cell, and this will be the thickness of the cell. So what will be the volume if we open it? If we open it like this, If we open it like this, or we can say like this, like this. So this will be the thickness dx and this will be the area. If we open this onion like this, so this overall surface will be the surface area and this part, this will be the thickness of the cell. So what will be the volume? Volume will be 4 pi x square into dx. So the value of Q enclosed, it will come out to be rho naught 4 pi x cube dx. And what will be the limit of integration? So here this x will vary from 0 to small r till the Gaussian surface. So it will be 0 to small r because we have to find the charge enclosed within the Gaussian surface. And what is the radius of the Gaussian surface? It is a small r. So the limit of integration will vary from 0 to small r. So this will be 4 pi rho naught will come out of the integration sign and this will be x raised to the power 4 by 4 0 to smaller, so it will be 4 pi rho naught into r raised to the power 4 divided by 4. This will get cancelled out and we will get rho naught pi into r raised to the power 4. Now we will put this value of this is a charge enclosed within the Gaussian surface of radius small r, so we will put this value here. So it will be rho naught into pi into r raised to the power 4 divided by epsilon naught. Now this pi and pi will get cancelled out, r square will get cancelled out, and we will get the electric field as rho naught into r upon 4 epsilon naught, rho naught into r square. This will be the electric field at point A inside the sphere. Now we have to find the electric field outside the sphere, that is r greater than capital R. So what will we do? We will choose a point C which will be at a distance of r from the center and we will choose a Gaussian surface which will pass through point C. Now we will again use the Gauss law, that will be E dot dA is equal to Q enclosed divided by epsilon naught. Now we know that I have already told you whether it is a solid conducting, non-conducting, hollow conducting, non-conducting sphere. If we have to find the electric field at any point outside the sphere, we can simply use the formula Q enclosed divided by 4 pi epsilon naught small r square. These things are okay, but what will be the value of Q enclosed here? We cannot directly use the formula rho into V because the charge density is varying as rho naught into R. Now earlier, in case of inside, we have seen that the Q enclosed was integration of rho naught 4 pi x cube dx. Now, in the case of inside, we have taken the limit from 0 to small r because the Gaussian surface was inside. Now, this time the Gaussian surface is outside the sphere. Now, what will be the limit of integration? It will be from 0 to capital R only. Why? Because within this Gaussian surface, the charge is distributed only in this sphere of radius capital R. That means charge is present from 0 to capital R only, not in this space. That means we can say the total charge enclosed is present within the limit of 0 to capital R. Now, if we use this integration, we will get rho naught and 4 pi as constant. That will be equal to x raised to the power 4 by 4 0 to r. So this will be 4 pi rho naught r raised to the power 4 divided by 4. Now this 4 and 4 will get cancelled out and we will get the value of charge enclosed as pi into rho naught into r raised to the power capital 4. Sorry, pi into rho naught into r raised to the power 4. Now, we'll put this formula in this equation. So we'll get electric field at point C. That will be rho naught into pi into capital R raised to the power 4 divided by 4 pi epsilon naught into small r square. So here pi and pi will get cancelled out and I will get the electric field as rho naught into r raised to the power 4 divided by 4 epsilon naught r square. Okay. This is the electric field at point C outside the sphere. Now we have to find the electric field at surface. So for surface, what will we do? R equal to capital R, we know that. So we will put small r equal to capital R in any of the equation and we will get the same formula. That means here electric field at surface that will be equal to rho naught into r raised to the power 4 divided by 4 epsilon naught into r square. Will put small r equal to capital R here. So here it will get cancelled out and we will get rho naught into r square divided by 4 epsilon naught. So this was all about the electric field due to spheres, whether it is solid conducting, hollow non-conducting or solid non-conducting sphere. Thank you.